When you're titrating a polyprotic acid, the general process is going to be almost exactly the same as that for a monoprotic acid. The main difference is that the pH curve is going to have multiple equivalence points, representing the multiple protons that can be removed from that acid. So we're going to look at a specific example, malonic acid, and draw the titration curve for malonic acid reacting with a strong base like sodium hydroxide. Malonic acid is an organic acid that has two carboxylic acid functional groups. It's what is known as a diprotic acid because it has two acidic hydrogens. And we're going to abbreviate it just as H2A for convenience sake. It is a generic weak acid with two acidic hydrogens. Before anything happens, if you just have a solution of that weak acid, you're going to have a low pH because you have an acid. And as you add base, eventually you will reach the equivalence point, where you've removed all of that first acidic hydrogen. At the halfway point, halfway to the equivalence point, you have pH equals the pKa. And more specifically, this is the first pKa, the pKa1. And this half equivalence point works exactly the same way as it does for a monoprotic acid. As you're beginning to convert H2A to HA-, you're going from a weak acid to its weak conjugate base, and you're building a buffer system. And halfway between having pure H2A and pure HA-, you have equal amounts of the conjugate acid and the conjugate base, which means you've got a buffer system with pH equal to pKa. Once you've fully converted everything to HA-, that will react with the added hydroxide ion. And halfway between equivalence point 1 and equivalence point 2, again, you're going to find a pKa value. This will be the second pKa value. And again, just like with a monoprotic acid, after you've removed all the acidic hydrogens, the pH will continue to increase if you continue to add base,